Hello there, Mr. Sutton here with the Pre-Cal Honors 510 Extra Practice Number 1 Solutions on Pythagorean Identities. For this first problem, we're trying to simplify this trigonometric expression. Now, there's no squared trig functions and not really much we can do algebraically, so really all there is to do is to turn everything into sine and cosine and hope for the best. Tangent, for example, I can express as sine over cosine. Cosecant is 1 over sine, so definitely could do something with those sines there in a minute. And then cosine, well, that's just cosine. Can't really do anything else with that. So we see here that these sine of x's can cancel. So can these cosine of x's. This cosine over here is really in the numerator. So that just leaves us with 1. It's about as simple as it gets. For this problem, there really isn't a whole lot we can do to simplify this other than turning everything into sine and cosine. Cosine of x is as good as it's going to get, but secant, that's really 1 over cosine. These cosines can cancel, so that's just going to leave us with 1 for this one. On this problem, to simplify this, notice that first we have this squared trig function. So we should always be looking for Pythagorean identities whenever we see squared trig functions. Do we have an identity with cosine squared in it? Well, we do. Sine squared plus cosine squared equals 1 is one of our identities. So we can get the pattern 1 minus cosine squared if we subtract cosine squared from both sides in this identity. That would give us sine squared equals 1 minus cosine squared. So that means that I can replace this 1 minus cosine squared with sine squared. And now once I've done that, let's see, this cosecant squared, I can make this 1 over sine of x. And it's not cosecant squared, just cosecant of x, but that's going to be 1 over sine of x. One of those signs can cancel with this sign down here. So then we just end up with sine of x times 1, or just simply sine of x. For this problem, there's no squared trig functions, but algebraically, we do still have the ability to FOIL or multiply these parentheses out. So that's going to give us secant squared minus 1. And then we do have a squared trig function now, so is there an identity with secant squared in it? Well, there is. 1 plus tan squared equals secant squared. So to get the pattern secant squared minus 1, I'd have to subtract 1 from both sides of this identity. That would leave me with tan squared over on the left side. So instead of writing secant squared of theta minus 1 over here, I can write tan squared of theta. To simplify this problem, the first thing I notice is that we have this squared trig function here. So just thinking about my little acronym PAX, the P in that, Pythagorean Identities, there's an identity that has cotan squared in it. 1 plus cotan squared equals cosecant squared. So I'm going to go ahead and replace this 1 plus cotan squared with cosecant squared. Now next, I notice that cosecant squared, that's really the same as 1 over sine squared. And that's awesome, because I can now cancel out this sign with one of these signs down here. So that just leaves me with 1 over sine of x. Now this isn't totally simplified because we still have a fraction. So I can still turn this into cosecant squared, and now I'm done. Trying to simplify this problem, it looks actually very intimidating when you first look at this, but it's not so bad. The key on this one is recognizing that you can factor this whole thing. So this is cosine to the 4th power. We have sine to the 4th power. What if I had cosine squared plus sine squared and I multiplied 2 of those together? Well, then I would get this exact expression here. So I can actually factor this into cosine squared of x plus sine squared of x, the whole thing squared. Now the reason this is really awesome is because cosine squared plus sine squared is none other than 1. That's our original Pythagorean identity. So I can just replace this whole thing with 1 squared, which is just simply 1. For this problem, I notice that I've got some squared trig functions, which is nice, but I can't really use any Pythagorean identities just yet. So what I am going to do instead is try to turn these into things that do not look like fractions. For example, 1 over cosine squared, I could make that secant squared, and 1 over cotan squared is really tan squared. And I do happen to have an identity that has both secant squared and tan squared in it. That's the 1 plus tan squared equals secant squared identity. So if I want to make this look like what I have here in my original expression, I can actually go ahead and subtract tan squared from both sides. That'll leave me with 1 equals secant squared minus tan squared, which means this whole thing just comes out to 1. To simplify this problem, it's kind of tempting to start by just multiplying all of this out, but we should always look first to see if we have any Pythagorean identities that we can easily apply. So for example, secant squared, that's in the identity 1 plus tan squared equals secant squared. And if I subtract 1 from both sides of this identity, I notice that tan squared is the same as secant squared minus 1. So I can replace this whole thing then with just tan squared of theta. Now over here, cosecant squared, that's part of the identity 1 plus cotan squared equals cosecant squared. And if I subtract 1 from both sides of that identity, I see that cosecant squared minus 1 is really the same as cotan squared of x. So I can replace this whole parentheses with just cotan squared of theta. Another nice thing here, cotan squared just so happens to be 1 over tan squared. So I can cancel out those tan squareds, and this whole thing actually just comes out to 1.